Welcome, curious minds, to another exploration with Investigating the Universe. Today we're setting our sights on the enigmatic world of quantum physics. The marvel we're spotlighting? The Quantum Zeno Effect. This intriguing phenomenon hints at the possibility of halting decay simply through observation. Imagine, if you will, a cosmic pause button that has the power to freeze time. Intrigued yet? Well, hold on to that curiosity, because we're about to delve into the nuts and bolts of this quantum quandary. We'll journey through the history of its discovery, explore the mechanisms that make it possible, and even touch on real-world examples of this effect in action. So brace yourself as we set off on this scientific sojourn. Buckle up as we unravel the enigma of the Quantum Zeno Effect, a phenomenon that allows us to freeze time, or at least the decay of quantum systems. Picture this. By merely observing a quantum system, we can halt its natural evolution. This is the Quantum Zeno Effect in action. It's a concept that might sound straight out of a science fiction novel, but it's very real and firmly rooted in the laws of quantum physics. To begin with, the Quantum Zeno Effect is named after Zeno of Elea, an ancient Greek philosopher known for his paradoxes about motion. However, the concept we're talking about here is a lot more than a philosophical conundrum. It's a mysterious phenomenon at the heart of quantum mechanics. Now let's try to understand it in simpler terms. Imagine you have a tub of ice cream in your freezer. You are eager to eat it, but you want to ensure it stays perfectly frozen until you're ready, so you keep checking on it. Every time you open the freezer and glance at your ice cream, it's still frozen. In a way, your continuous observation prevents it from melting. The Quantum Zeno Effect works on a similar principle. In the world of quantum physics, particles exist in multiple states at once. However, when we observe these particles, they collapse into one state. The Quantum Zeno Effect suggests that if we observe a quantum system continuously, we can prevent it from changing its state or decaying. In essence, our observation acts like a pause button, freezing the system in its current state. But remember, we're dealing with the mind-bending world of quantum physics, where things aren't as straightforward as they seem. The Quantum Zeno Effect isn't about literally watching particles. Instead, it's about the act of measurement, which in quantum mechanics can be an interaction with other particles or systems. So, as fascinating as it sounds, the Quantum Zeno Effect is not about using your eyes to freeze time, but rather, it's about how interaction at the quantum level can influence the state of particles. Now let's delve deeper into the mechanics of this fascinating phenomenon. To truly appreciate the Quantum Zeno Effect, let's take a quick trip back in time. This fascinating concept wasn't simply plucked from the ether, it's the fruit of intense intellectual labor, born from the minds of pioneering physicists. The name Quantum Zeno Effect was first coined in the late 20th century by two such physicists, George Sudarshan and Baidyanath Misra. But the seeds of the idea were planted much earlier in the fertile ground of quantum theory. Sudarshan and Misra put forward a tantalizing proposition that continuous observation could inhibit the decay of a quantum system. This idea was initially met with skepticism, yet as time rolled on, experimental evidence began to support their bold claim. Today, the Quantum Zeno Effect is a recognized facet of quantum mechanics, a testament to the dogged determination and innovative thinking of Sudarshan and Misra. Understanding the historical context enhances our appreciation of this mind-boggling phenomenon. Now, let's unravel the mechanisms behind the Quantum Zeno Effect. In the world of quantum physics, particles don't have definite states until they are observed, a concept known as superposition. When we observe these particles, we force them to collapse into a single state. The Quantum Zeno Effect suggests that if we observe a quantum system continuously, we can prevent this collapse, effectively freezing the system in its initial state and halting decay. To understand this, imagine a particle that can exist in two states, decayed and undecayed. In a standard quantum scenario, the particle has a certain probability of transitioning from the undecayed state to the decayed state over time. However, each time we observe the particle, we reset the clock, so to speak, causing it to remain in its undecayed state. Now, you might be wondering, what does observation mean in this context? In quantum physics, observation doesn't just mean looking at something. Instead, it involves interacting with the quantum system in a way that generates information about it. This interaction can be as simple as bouncing a photon off a particle, or as complex as a full-blown scientific experiment. So how does observation halt decay? It's all about the interaction. When we interact with a quantum system, we disturb it, forcing it to choose a state. If we do this often enough, the system doesn't have time to evolve or decay. It remains stuck in its initial state. It's a bit like repeatedly flipping a coin and catching it before it lands. The coin never gets a chance to show heads or tails. It's always in a state of flux. The implications of the Quantum Zeno Effect are profound. It challenges our understanding of reality, suggesting that we can influence the universe simply by observing it. Moreover, it opens up exciting possibilities for quantum computing and other advanced technologies, where manipulating quantum states could be key. Get ready to journey into the heart of this quantum quirk. To bring the theory to life, let's dive into real-world examples and experiments. Quantum Zeno Effect isn't just a theoretical concept, it's been observed in the real world, from atoms to photons. Let's take a look at an experiment conducted by physicists at the University of Innsbruck. They utilized trapped ions and laser beams to observe the Quantum Zeno Effect in action. The ions, when left alone, would naturally flip their spin. But when the physicists continually observed the ions, the flipping was halted, a real-life demonstration of the effect. On a larger scale, consider the decay of light particles or photons. In a study by the National Institute of Standards and Technology, researchers found that by frequently measuring the state of the photons, they could extend their lifetime, effectively slowing their decay. These examples connect the dots between theory and practical applications. They hint at potential futuristic technologies like quantum computers and atomic clocks that could stem from this phenomenon. We'll connect the dots between theory and practical applications, hinting at the potential futuristic technologies that could stem from this phenomenon. As we wrap up our quantum odyssey, we've glimpsed the extraordinary world of the Quantum Zeno Effect. We unraveled the enigma of how simple observation can halt the natural decay of quantum systems, akin to keeping your ice cream frozen with just a glance. We journeyed back in time to appreciate the rich history and pioneering minds that contributed to its discovery. We delved deep into the mechanisms behind this fascinating phenomenon and explored its real-world applications, hinting at the potential futuristic technologies that could stem from it. The universe is indeed a mysterious place, and quantum physics continues to astound us. If this exploration piqued your curiosity, showed you something new, or simply kept you entertained, don't forget to hit the like button. Subscribe to our channel for more mind-bending journeys into the universe. Share your thoughts in the comments below. We're eager to hear your insights. Stay curious, stay inspired, and until next time, keep investigating the universe with us.